Now, the other thing that we need to look at is how we can get aldehydes and ketones from acid chlorides. So we know before that we've seen this, at least before, that LAH is more reactive than NABH4. Right? And that has to do with the electronegativity of boron being greater than that of aluminum. So with that bigger electronegativity, remember it pulled electron density away more from the H, which reduced its delta minus character. In other words, it made it have a larger delta plus. So the reaction that we've seen before takes a carboxylic acid and adds LAH, and in a very slow reaction it makes an aldehyde, and the reaction cannot be stopped there. Instead it continues on, and the second step of this reaction is very fast, and we form an alkoxide. So what we end up getting over here is an alkoxide. So the question is, how can we stop this reaction? Well, if we wanted to stop here, for example, at the aldehyde, what we need to do is we need to use a source of hydride that's less reactive. So what we're going to do, and this is what our book does, is we use a milder reducing agent. We use lithium aluminum tri-T-butoxyhydride. So what we do is we put big R groups here with electron withdrawing properties. So we're pulling electron density away, right? So that's rendering the H of LAH a little less reactive. So we get this steric hindrance up here at the top, and we also end up having less reactivity because of the T-butoxides. So that's the first thing that we're going to do. And the second thing that we're going to do is that first step, remember, when we had the carboxylic acid and LAH, that was a slow step. So we're going to start off with something more reactive. So here we have our acid chloride. So let's take a look at how this reaction is going to take place. So the overall reaction looks something like this. So, right, we have our acid reacting with thionyl chloride to become our acid chloride, right? Now the mechanism for this is actually pretty straightforward. So there's a couple interesting little steps in it, though, that are different than things that we've seen before. So let's take a look at this. Let's start off with here a carboxylic acid. Right, now, by the way, we're going to see this reaction again in chapter 20 and 21, where we deal with carboxylic acids. And then let's put in thionyl chloride here. So what we're going to do here first, remember, if you're trying to figure out what's going to happen here, that sulfur has a pretty good delta plus charge on it because you have all these electron withdrawing groups hanging out near them. Now we want to have one of these two oxygens react. We're going to pick the oxygen that generates the most stable intermediate, has the most resonance structures. So that oxygen is going to be more basic than the oxygen that's connected to the H down here. So that's going to give us an R, carbonyl, sulfur here. Right, that sulfur is going to have an oxygen with a minus charge on it, a chlorine plus charge here, and then an OH down here. And then that's going to give us a few resonance structures here, guys. So let's draw them out. That gives you your R group, your carbon, oxygen, and all that other stuff. Right, and then the last resonance structure there would take the electrons from the OH to make a double bond here. So that'll give us our R group, our carbon, our O minus up here, our chlorines, and then double bond H like this. So this next step here is going to take care of kind of this mess that's happening up here. So we're going to take a set of those electrons, swing them down, and we're going to kick off chloride. That'll give us this intermediate here. Our chlorine back in there, and then here's your OH. Plus charge there. Now that is going to get deprotonated, so we're going to lose this H here. And our book uses chloride to do that, so we'll stick with what the book's using. So we're going to grab that H, and then we're going to get this neutral molecule. So you'll have your R, chlorine, just like so. All right, now the last step, the second to the last step here is chloride's going to come in here and it's going to attack that carbon. So we're going to swing around and do this. Well, that'll give us our R group, our carbon, chlorine, and then down here we're going to have our chloro and then an O minus here. Right, so we're almost done. We have one last step, and it's kind of a lengthy step here. And this is one of the things that makes this kind of a cool reaction. So we're going to come over, and we're going to do this. That's going to give us our carbonyl back. Now, that bond's going to swing over here, and then we're going to kick off chloride. So that's going to give us as our final products here an R, C, double bond O. I'm going to swing that chloro group up here. All right, and then we're going to get SO2. And SO2 is a gas. That's what that arrow up means. And Cl minus. Sometimes books will write HCl in there. All right, so in the end, we end up getting our acid chloride. So this reaction is another reaction that we're going to see a lot throughout the rest of the semester, because these are very reactive and they're very useful for multi-step synthesis. So as far as multi-step goes, kind of the pattern that you're going to see here is this, is you're going to have SOCl2 with a carboxylic acid, and then if we wanted to take that a step further, we could have this primary alcohol with Jones. So that's kind of the pattern that you end up seeing for multi-step synthesis. And what that does, again, it takes you to your acid chloride, and then it takes you into your aldehydes. Well, it turns out that acid chlorides are reactive towards nucleophiles. So we'll see that in more detail when we get into those reactions in those chapters. It's chapter 20 and 21. But I want to show you one here, and that is the reaction of an acid chloride with Grignard. So here's our acid chloride. Right. When we add a Grignard reagent to this, remember that reacts like it's an R minus essentially. You end up forming a ketone, and the reaction can't stop here. It continues. So we're not able to isolate that ketone. Instead, it happens again, we get another addition. This forms an alkoxide, and then that alkoxide through an acid workup can form an alcohol. So then the question is, how can we stop the reaction at the ketone? Well, just like we wanted to try to stop the reaction at the aldehyde, where we added the LAH and we changed that to a less reactive species, we need to have a less reactive species than a Grignard. So the solution here is to use this thing called a lithium dialkyl cuprate. Let's take a minute and talk about how it's prepped, why it's less reactive, and then look at some reactivity here too. All right, so the way that we prepare lithium dialkyl cuprates is you take acid chlorides and you add an R'2 CuLi to it, and that will make a ketone. So that's how we end up stopping that reaction. Now, the dialkyl cuprate itself is prepared by the reaction of two equivalents of that organolithium reagent with copper iodide. And the way that we make organolithium reagents is that we take our alkyl halide, we add lithium, and you get RLi, and then we take that, we add CuI to get R2CuLi. Okay. Now, let's talk about why this is less reactive than a Grignard reagent. So the reactivity of the lithium dialkyl cuprates is less than that of a Grignard reagent because of electronegativity. So copper is more electronegative than magnesium. So we can see those numbers listed up above. So when we have an R, it's really two R groups, right? But we can write it like this. But when we have those R groups connected to copper, because it's more electronegative, it pulls electron density away from our alkyl groups more. And it's those electrons that are on that R group that are rendering it as a nucleophile. Right? So because magnesium is less electronegative, it leaves a larger delta minus on that carbon. Right? So what we're going to see is something like this below. So here you would have an alkyl halide. So that's your R group there. Right? So we'll put that in here. So there's your R, Cl. And reaction-wise, you're going to see this as two steps. One, Li, that's going to make your organolithium, and two, Cu, I. Right, so what we form over here, and this is just another way of writing it, but this is really an R2CuLi. And then we'll add that to an acid chloride, and then the reaction will continue through a nucleophilic addition, but it would stop at the ketone here. So the reaction, and we ought to put that in our notes, this reaction stops here. All right, so let's take a look at carb anionic nucleophiles. So it's nucleophilic addition of hydrogen cyanide, or cyanohydrins, that we'll take a look at first. So reaction fairly straightforward here. Hydrocyanic acid plus water, and this is an equilibrium arrow here, gives us H3O plus and Cn minus. Cyanide's a strong base. It's a good nucleophile. Okay. It's going to react rapidly with carbonyl compounds, and it produces compounds called cyanohydrins. So cyanohydrins are these guys here. And the reaction is fairly straightforward if you look at the mechanism. Right, you get nucleophilic attack on our carbon, generating this tetrahedral intermediate. Now that's going to get protonated down here with HCN to give you your cyanohydrin. Like hydrate formation, it's an equilibrium type of a reaction, and we know reactivity of aldehydes versus ketones, and we can see the reverse of this reaction is pretty straightforward too. So if you have a generic base, then you would reform an oxygen with a minus charge, and then you'd kick off cyanide down here at the end. Now, the newer editions of our textbook, the 9th edition in particular, introduces this new chemical called dibal. It's dibal-H. It stands for diisobutyl aluminum hydride. So I wanted to show you the observed reactions here. So if you take a nitrile and then add dibal-H and H3O plus with water, you end up getting this intermediate. It's like an imine, right? And then the addition of H3O plus takes it to an aldehyde. So that's an important reaction that we're going to see for multi-step and an observed reaction here too. And the other thing that we can do is we can take acid chlorides, we can use dibal and get the reaction to go to aldehydes in a similar way that we use the lithium aluminum tritibutoxyhydride. And then esters too. So over here we have an ester with dibal-H and H3O plus, taking us over here to our aldehyde. So a lot of those reactions are going to be seen in chapter 20 and 21 also as far as multi-step synthesis goes. And then the last one just to mention here before we look at this next type of reaction is the addition of acetylide ions. We've already seen organometallic reagents, but the acetylide ion would add to our carbon and then it would get protonated, right? So if you're looking at that reaction down here below, you'd have here an O minus with your right? A satellite ion here, H3O plus, we'll just protonate that down there at the end.